Today I want to be focused on polynomials in one variable. Okay. Well, suppose F is a field. I want to consider the ring of polynomials with coefficients in F. So this is our main ring for today. I want to discuss its properties. Just in case, an arbitrary element here is just a picture. And we have some formal rules for addition and multiplication. I believe I can skip the formulas because the formulas were presented during the previous lecture. But today I want to recall that we also have another ring, which is the ring of functions from F to F, which consists of all functions from F to F. This is also a ring, because we can add and multiply functions pointwise. So if we have two functions, phi and psi, then what is the sum of the functions? Well, the sum of the functions, by definition, acts like this, and the product of the functions acts like this. This is just by definition. So this is also a ring. By the way, what is the zero element of this ring? The zero element, not identity, it's zero. The neutral element with respect to addition.
Something that goes to zero.
What again?
Something that goes to zero.
Well, it should take every element to zero. So the constant function which takes every element to zero is the zero element of this ring. Okay, and the identity element of this ring is the function which takes every element to 1. Because indeed, if we take a function phi which takes every x to 0, then 0 plus psi of x will be psi of x, so phi plus psi will be psi. So such a function will be a neutral element with respect to addition. And if phi takes every element to 1, then it will be a neutral element with respect to multiplication. So this is also a ring. So we have a ring of polynomials, which consists of these pictures, and we have a ring of functions, which consists of the functions from F to F, and we have a homomorphism from the first one to the second one. So if we have a polynomial, let's say, then we can produce a function. I want to denote a function as f with a hat in order to distinguish the polynomial and the corresponding function. So well, it's clear what it does. So it uses this formula in order to produce a map. So f with a hat, it takes an element, let's say a, from the field f to the element f of a. So it's just a function which substitutes its argument to the formula of the polynomial. Well, one can check that this map is a homomorphism. So this is a homomorphism. A homomorphism of rings. So it preserves addition, multiplication, and the neutral element with respect to multiplication, which is identity. But what is important, this homomorphism need not be injective. So this guy need not be injective. So by definition, equality here means equality of the coefficients of the polynomials. So the polynomials are just formal expressions. If the formal expressions are not the same, the polynomials are not the same. The equality here means the equality at all possible points. So two functions are the same if they give you the same result for the same input every time. But it may happen that you have two different polynomials which produce exactly the same functions. So the reason why we need these formal polynomials because of this effect. Well, it's not enough in algebra to deal with functions. We need these formal polynomials. And one of the reasons why we need these formal polynomials, because, during the next lecture, we will discuss fields and finite fields. And, what is important is to produce, a specific finite field. So you have to use some tools in order to construct a new field. So basically, there are several ways how to produce a new ring or a new field. And the ring of polynomials, they provide some universal tool how to produce like any ring you want. In particular, you can produce any field you want using polynomials in one variable. So you will see how it works, but in order this to work, we need the formal definition of the polynomials and not the functional definition of the polynomials. So that's the reason why we use these formal tricks. Okay. And one additional remark. This happens in case the field F is not infinite. And this will be our main case. So when we will discuss finite fields. Okay, now what should be next? The next thing, let me recall that if we have a polynomial, then the degree of this polynomial is the highest power with a non-zero coefficient. And in general, if we multiply the polynomials, the degree will be the sum of the degrees. Well, it looks simple, but it's not true in a general polynomial ring. So if you take an arbitrary polynomial ring with coefficients in an arbitrary ring, just a commutative ring, then what happens, the degree of the product is not higher than the sum of the degrees. But in our case, the coefficients, they belong to a field. And in case of a field, this happens. And the reason why this happens is because in a field, we do not have zero divisors. So if we multiply the highest coefficients, then if they are not zero, the product is also not zero. But in arbitrary ring, when we have zero divisors, it may happen that the leading coefficient dies because when we multiply the leading coefficients, well, even if they are not zero, the product could be zero. So that's why, in general, we just have this inequality. So this is a special thing for rings without zero divisors. By the way, there is one thing I should say here. This is almost a definition. There is one special case where this definition doesn't work. The case of a zero polynomial. So if all the coefficients are zero, there is no non-zero leading coefficient. So in case of a zero, we will say that the degree is minus infinity. So the polynomials, so the constant polynomials, the polynomials without a variable, they have degree 1 or the degree 0 or minus infinity. So minus infinity is a special case of the zero polynomial. Well, there is a reason for that. There is a theory of valuations on an arbitrary commutative ring. And each valuation, well, this is an example of a valuation. The degree is an example of a valuation. And each valuation produces, a norm on the ring, which somehow measure a length of an element of a field. Well, if you want the length of the zero polynomial to be zero, this is the definition you want to use. Because the length is defined let's say 2 to the power of the degree. So if you raise 2 to the minus infinity, you will get 0. So this is, well, I mean, there is a general theory, and if you want to be consistent, this is the definition you want. So basically, because you want somehow the length of the polynomial to be something like 2 to the power of the degree of f. And you want the length of the zero polynomial to be 0. Okay. What should be next? Okay, this is clear, this is clear. Again, there is also a Euclidean division algorithm in the ring of polynomials. Who is familiar with the Euclidean division algorithm in the ring of polynomials? Euclidean division. Okay, so suppose we have two polynomials, f and g, from the polynomial ring, and f is a field. So it's important. This theory doesn't work when f is something else but a field. Now, what does it mean to divide a polynomial f with a polynomial g with some remainder? Well, it means that we want to present f as the following sum: q times g plus r, where the degree of r is strictly smaller than the degree of g. If we can represent f in this form, we will say that we divided f by g with the remainder r. So this is a remainder. And this is a quotient. So this is the same as in case of integers, but in case of integers, the property for the remainder is the module of the remainder is strictly smaller than the module of the divider, okay? But here, instead of the module, we use the degree. So we want to divide f by g, but it may happen that, well, f is not divisible by g. So we will represent f like g times something plus something smaller than g. And the way to explain that r is smaller than g is to say that its degree is strictly smaller than g. Okay? If r is 0, we will say that g divides f. So if r is equal to 0, then we will say that g divides f, or there is another notation, f is divisible by g. Okay, who's familiar with this representation? Okay. So you know what the division with remainder in the ring of polynomials is. Okay, now, what should I say about this thing? Okay, GCD. Let me define the GCD formally here. So suppose we have two polynomials. Now, what is the greatest common divisor? The GCD, let's say D, is the polynomial with the following properties. The property number 1, D must divide F and G. So it's a divisor of these two guys. The property number 2, it must be, well, the greatest divisor in the following sense. If we have any other divisor, so for any other divisor H, it follows that H divides G. So this is somehow, so the division defines an order. So we say that G is larger than H if H divides G. This is how you should interpret this thing. And the third property, the leading coefficient of D must be 1. So this property, well, there is a term for this property. It means that D is monic. So monic means the leading coefficient is 1. Yep.
I think there must be H divides D, no?
Oh, yeah, thank you. That was a mistake. You're right. Yep, exactly. So again, so D must be a divisor, and for any other divisor, H must divide D. So in this sense, D is the largest possible divisor, and if we find such a divisor, there is an option to change its leading coefficient by multiplying by any element of the field. So we want to normalize it and to have the leading coefficient to be 1. So, okay, so this is the definition of the greatest common divisor. Well, this definition must be unique. So what should be next? Yeah, and by the way, there is a remark. So let's say we deal with polynomials with rational coefficients. So let's take 2x and x. So this is your f and this is your g. Is it, let's say, this is your f and this is your g. Is it true that g divides f? It's true. Is it true that f divides g? Again?
Yes.
Exactly. Because this is the coefficient in a field. So why, well, it's clear why g divides f, because, well, in order to this to happen, we need to represent f as a product of g and something. And here is g times something. But if you want to show that g is divisible by f, so you need to represent g as f times something. So it will be 2x times 1 over 2. Since every coefficient is invertible in the field, so it doesn't matter. If you multiply your polynomial by a non-zero coefficient, well, you don't change this property that your polynomial divides something else or not. So be careful, don't forget that your coefficients are invertible, so it doesn't matter if it's 2 or something else here. So for example, you can write something like 25 over 3x, it divides x squared plus x, or something like that. So it's easier to deal with polynomials without these fancy leading coefficients, but it may happen that you have something here instead of 1, but it doesn't change this property. Okay, and another example, another remark. Let's say I take an arbitrary polynomial and I want to define a GCD of f and 0. What will be the GCD? Again? Okay, other options?
Maybe.
F. Okay, there are two options. Are there any other options but 0 and f? Okay, so who thinks that the correct answer is 0? Okay, who thinks that the correct answer is f? Okay, you see, by voting, the correct answer is f. But let's check why the correct answer is f. Because let's check that f, first of all, let's check that f is a divisor of f and 0. Well, it's clear that f divides f. But f also divides 0 because 0 equals 0 times f. It means that f divides 0. But so it's a common divisor of f and 0. But it's not true that 0 divides f, because you cannot represent f as something times 0, because the product will be 0. So if f is not 0, it's not true that the GCD is f. So somehow you should think as 0 is a polynomial divisible by everything. So it doesn't change the GCD when you add the 0 polynomial. So yeah, so this is a corner case more or less. So be careful when you have something and 0, the GCD is this something. So if f is 0, this formula is also true. Okay. Another remark. Okay, now, as usual, let's start discussion of the ring of polynomials with description of the ideals of this ring. And then we will use this description further. So the claim, suppose we have a polynomial ring with coefficients in a field, and suppose I is an ideal. Then there is a polynomial f such that I consists of all polynomials divisible by f. And there are two different notations for this type of ideals. The first notation is this one, so basically f times everything, or the other notation is f in parentheses. So the situation is exactly the same as in the case of integers. So in case of integers, as you remember, if we take an ideal of the ring of integers, this ideal consists of all integers divisible by a fixed one. Here the situation is the same. Every ideal, for every ideal you can find a polynomial f such that all the polynomials here are just all the polynomials divisible by f, and that's it. So this is the full description of all possible ideals. And it's clear if you take a subset of this form, it's an ideal. Okay, but so this is the claim. Other questions related to the statement itself. Should I clarify the statement? Okay, the next question, who remembers the definition of the ideal, the properties that we need to check? Who thinks that we should recall the properties? Okay. By the way, who remembers the definition of a ring? Okay. And who doesn't? So for those who doesn't, just in case. So, well, basically what is a ring? Is a set with two operations, addition and multiplication. And they are well behaved. This is like, if you don't want the details, this is everything you need to know. So you have just a set of elements and you can add and multiply them together, and the rules are more or less natural. This is what the ring is. Now, so what is an ideal? So let me recall. An ideal is a subset with the following properties. The subset must be an additive subgroup. So I plus, so if we forget multiplication, then this subset with respect to addition must be a subgroup in the ring with the addition. This is the property number one. And before we're moving to the property number two, who remembers the definition of a subgroup? What kind of properties should we check? Is there anyone who doesn't? Okay, so there are three properties. The property number one, we should check that the neutral element with respect to addition is in our subset. The property number two, if we have two elements, x and y, in our subset, then there's sum in our subset. And the property number three, if we have an element in our subset, then its inverse with respect to addition must be in our subset. So minus x must be in I. Okay? So these three properties, they're equivalent to be a subgroup. So this is just a definition. Okay, and that was the property number one for being an ideal. And the property number two for being an ideal is the following. If we have an arbitrary element x from the ideal I, an arbitrary element R from the ring f of x, then their product R times x must, x is not a great choice for a name of the element. So let's say y, because x is reserved here. I'm sorry. So if we have an arbitrary element y in the ideal I, an arbitrary element R in the ring of polynomials, then their product must be inside the ideal. So if you multiply, it's like zero. So the ideal behaves like zero. If you multiply anything by an element from the ideal, you will get an element from the ideal. So this is how you should think about the elements of the ideal. It's like extended zero. Okay, So this is what we need to check in order for something to be an ideal. Again, so now let's say we will take a subset of this form. So we fix a polynomial f, and we take all the polynomials divisible by f. So the polynomials represented in this form. Well, it's clear that all these properties are satisfied. So if we take h to be 0, then we will have 0 in this set. If we have two polynomials divisible by f, then their sum is divisible by f, because we can like move out the factor f. And if we have a polynomial divisible by f, then it's the minus this polynomial is also divisible by f. So these three properties are satisfied. And if we multiply something divisible by f by something else, we will get something divisible by f. So this subset is indeed an ideal. Now, well, this was more or less the arrow in the opposite direction. So now we want to show that there are no other ideals. So if we take an arbitrary ideal, it will definitely have this form, okay? So let's take an arbitrary ideal. And we want to find this polynomial f. Now, by the first property, 1a, we know that there is a 0 here. Now there is the options. The option number 1, there is nothing else here, just 0. And the option number 2, there is something which is not 0. Well, if this is true, then, then our ideal consists of all elements, divisible by 0, let's say. So we should take f to be 0 in this case. Well, everything divisible by 0 is just 0 itself, because 0 times anything will be 0. So this option is clear. Now, let's take a look at the second option. So we know that there are non-zero polynomials in our ideal. Okay, so if we have a non-zero polynomial, we can find a non-zero polynomial with the smallest possible degree. Well, because it's clear because the degree belongs to the set of natural numbers, and there is always a minimal element for every subset here. So let's say f is an element of I such that the degree of f is the smallest possible for a non-zero polynomial. So the only polynomial in I with a smaller degree is the 0 polynomial. All the other polynomials have the same degree or higher. Let's show that every polynomial in I is divisible by f. Okay? Now, let's take an arbitrary polynomial g from I, and I want to divide g by f with the remainder. So it's always possible to do. So we can represent g as the sum of the product q times f and the remainder r, and the degree of the remainder is strictly smaller than the degree of f. Now, if we rewrite this equality as r equals g minus q times f, then by the choice, g belongs to I. Again, by our choice, f belongs to I. Since I is an ideal and q is an arbitrary polynomial, then this product is also in I. And since I is an ideal, the difference between two elements from the ideal is also inside the ideal. So as the result, the element r must be also inside the ideal I. But you see, the degree of r is strictly smaller than f, and f was the smallest non-zero, was the polynomial with the smallest non-zero, among the non-zero polynomials, it was the polynomial with the smallest possible degree. So if we find a polynomial in the ideal I with a smaller degree, the only option for R, well, is 0. So by definition of F, by the choice of F, and this fact, we see that R is 0, which means that G is divisible by F. So we have proven that every element of I is divisible by F. So that's why we covered the case number 2. Who was able to follow? Who requires any kind of explanation, or should I repeat something? Okay. Now, what are the consequences of this claim? Just in case, should I say something else? No. So let me show you several corollaries. So again, so we have the polynomial ring, and we have two elements here. Should I? Okay. First of all, let me clarify that GCD exists and unique. So GCD exists and unique. And the second thing, there are polynomials U and V such that GCD of F and G equals U times F plus V times G. So the same properties as we have in case of integers. So in case of integers, GCD must be, well, it must exist and it's unique. And also we have this trick that if we have a GCD, then you can represent GCD as a linear combination of the initial two elements. So the same thing happens here. So the properties of the polynomials, they are very similar to the properties of integers. Okay. Now, let's, by the way, who thinks that the first one is clear? Okay, who thinks that the second one is clear? Okay, is there anyone who thinks that some of this is not clear or it requires an explanation? So we can skip the proof. Okay, who doesn't want to skip the proof, just in case? Okay. Then I have a question to you. How to prove this one? Why this is true? Well, if it's clear, then there must be an argument. Okay, so let me show you the argument. So let me start with the second one. I believe it's easier. You see, we have proven that every ideal in the ring of polynomials consists of the polynomials of this form, divisible by some fixed polynomial f. So let's use this fact. So how to use this abstract fact in order to prove this statement? Well, let's define an ideal, the following set of polynomials: u times f plus v times g, where u and v are in the ring f of x. Okay? So this is a subset of polynomials. Well, I claim that this subset is an ideal. Who can see this? Okay. So this is an ideal. Okay, in order to check that this is an ideal, we need to check these properties. Okay? So let's start with the property number 1. We need to show that 0 belongs to this subset. But if we take u and v to be 0, then we will get 0 here. Okay? Now, let's take two elements of this form, like uf plus vg and u prime f plus v prime g. If we add them together, we will get an element of the same form. So this subset is closed under addition. And also, if you take a minus here, you just replace u by minus u and v by minus v, and you will get an element of the same form. So the property number C also true. So it's an additive subgroup of f of x. And then, if you multiply this expression by any polynomial, like something h here, then you just replace uh by u and vh by v, and you will get expression of the same form. So the property number 2 from the definition of the ideal holds. Okay? Who was able to follow? Okay, so now it should be clear that this is an ideal. But now we have this statement that every ideal has a special polynomial f. Well, this polynomial need not be unique, but it has a polynomial f such that all the elements of the ideal have this form. Okay? So there is a polynomial d such that I equals this. So it consists of all polynomials divisible by d. Now, let's check that d is a GCD and it's represented in this form. Okay? First of all, it's clear that d is represented in this form. Who does agree with me? Who thinks that I should clarify this part? Okay, so d is just an element of I, so it's represented in this form. So we just need to show that d is actually a greatest common divisor. Okay? Now, for that, we need to show that d divides f and g. We need to show that every divisor divides d. Well, and then we can switch to d with the and then we should switch to the monic d. So if the leading coefficient of d is not 1, we can multiply d by any coefficient, and well, it doesn't change the ideal on the right. So we may switch to the d to the monic d. Okay, now so we need to check the first two properties. Okay, so what does it mean that I equals to this thing? It means that every element here is divisible by d. But if we take u to be 1 and v to be 0, it means that f belongs to this ideal. And if we have u to be 0 and v to be 1, we will get that g belongs to this ideal. And by definition, everything that lies here is divisible by d. So d divides f and d divides g. So that's why the property number 1 holds. Who was able to follow? Are there any questions, or should I repeat the claim? Is it clear? Okay. Now, the second part. Suppose we have h, and this element h divides f, and h divides g. We want to show that h divides d. But since d is an element of I, and every element of I has this form, then d can be presented as u times f plus v times g. And now you see h divides f, so h divides the first summand, and h divides g, so h divides the second summand, so h divides the whole sum. So that's why h divides d. So from this, it follows that h divides d. So the first two properties are satisfied. And if we want to satisfy the third one, we just need to cancel the leading coefficients here, and we will get the greatest common divisor. So that's why the second claim holds. Are there any questions? It's so quiet today. I hope because it's clear and simple. Okay. By the way, well, let me clarify what we did here. What we actually did here, we produced a polynomial d such that this polynomial divides f and g, and it's divisible by any other divisor. So what we did here is simply we proved the existence of the greatest common divisor. Okay? So because, well, we take this ideal, it's generated by some monic polynomial d in this sense. So this d is the greatest common divisor as we checked. So the existence of the greater common divisor follows from the second claim. Now the uniqueness. Suppose we have two greatest common divisors, d1 and d2, are GCD of f and g. Well, since this is the greatest common divisor and this one is just a divisor, then d1 must divide d2. So d1 divides d2. So d2 can be presented as something, let's say, phi times d1. From the other hand, since d1 is the greatest common divisor and d2, well, maybe considered as just a divisor, then d2 must divide d1. So d1 must be psi times d2. Now we can substitute this thing into here, and we will get d2 equals phi times psi d2. Then we can move everything to the left and write it d2 times 1 minus phi times psi equals 0. But now, this may happen only in case one of the polynomials is 0. Why? Because we have property for the degree. The degree of the 0 polynomial is minus infinity. So, and the degree of the product is the sum of the degrees. So if these guys are not 0, the degree is strictly greater than minus infinity, and the sum of the degrees is strictly greater than minus infinity. So one of them must be 0. So the only option, since this guy is not 0, the only option is this one 0. So, but this means that 1 equals phi times psi. So phi and psi are invertible polynomials. But what are the invertible polynomials? Again, these are non-zero polynomials, and the degree of phi plus the degree of psi equals 0, the degree of 1. And again, since they're non-zero, well, because d1 and d2 are non-zero, these are natural numbers such that the sum of natural numbers is 0. So the only option for these, they are both 0. So that's why these are polynomials of the 0 degree. So they're just numbers. So these are non-zero numbers. So phi and psi are non-zero numbers. So that's, but from the third property, we know that the leading coefficient of d1 and d2 is 1. If we multiply the leading coefficient of d1 by the coefficient phi, we will get phi here, but it means that phi must be 1. And the same argument says that psi must be 1 because of the third property of the greatest common divisor. So since d1 and d2 are monic, phi and psi are equal to 1. So that's why d1 and d2 are the same. So this completes the proof. Who was able to follow? Okay, are there any questions regarding the proof? Okay. Now, let me show you another example of the application here. So how to compute the greatest common divisor? There is a very simple algorithm, which is based on the Euclidean division algorithm. So if you have two polynomials, f and g, then GCD of f and g equals to the GCD of g and f minus hg. So let me check. Who thinks that it's clear? And who can prove this? Well, you know, the set of hands raised on the first question and the second question must be the same, because it's the same question, just in case. Well, okay, how to prove that the GCD here equals the GCD here? Well, we should show that every divisor of f and g divides g and f minus hg, and vice versa. If the set of all the divisors for this pair is the same as the set of all divisors for this pair, then the greatest divisors are also the same, because they're just on the top of this set of divisors, okay? So if we take something which divides f and g, well, then it divides g, because it divides g. And since it divides f and g, then it divides this expression. Vice versa. If we have something which divides g and this expression, then g can be rewritten, not g, f. F can be rewritten as f minus hg plus hg. So if we have something which divides these two polynomials, then it divides hg and f minus hg. So it divides f. So if something divides this pair, then it divides this pair, and vice versa. So the set of all divisors for these two pairs is the same. So that's why if you take all these divisors and you take the greatest one among the divisors, they are also the same. So that's why these two GCD are the same. Who was able to follow? Okay. No? It's fine. Okay. But now, how do you compute the greatest common divisor now? Here is an algorithm. So you take two polynomials, f and g. Then you divide f by g with the remainder. So you write something like this. Okay? So r is equal to f minus q times g. So by this formula, the greatest common divisor of f and g equals to the greatest common divisor of g and r. Because r is f minus g times something. And now you can repeat this procedure. Now you should divide g by r with the remainder. So you divide it with the remainder, and then you shift r to the left and replace r by the remainder r1. So you pass to this thing. And so on. So you divide the left one by the right one with the remainder, then you shift the right one to the left and replace it with the remainder. And when should you stop? Well, you will stop at the moment when the second argument is 0. And in this case, as we already know, the greatest common divisor is d. So the algorithm is exactly the same as you use for the integers. But now you just deal with the polynomials. Okay. And yeah, there is an extended Euclidean algorithm which works exactly the same way as for the integers, and you can even find these u and v explicitly. But I don't want to discuss it here. Now, unique factorization domain. UFD. Unique factorization domain. F of x. Let me explain what it means. Well, domain means no zero divisors. Unique factorization, well, I will explain you what it means. in a second. So, but basically, in case of integers, there is a notion of a prime integer, and you can represent every integer as a product of primes in a unique way, and probably plus minus 1. So the same happens here. So let me start with the definition. So first of all, we need to define something which is analogous to a prime number. So first of all, we can split every polynomial into two categories. Every polynomial is either invertible or non-invertible. Okay, and so we don't discuss invertible polynomials here. So let's say f from f of x is not invertible. Then we will say that f is reducible if we can represent f as a product of two polynomials, h times g, and the degree of h and the degree of g is strictly smaller than the degree of f. And by the way, if we say that the degree of both polynomials are strictly smaller than the degree of f, the degree of g and the degree of h, they cannot be 0. So they cannot be constant, because if the degree here is 0, the degree of g must be equal to the degree of f. So actually, we also have this. In this case, f is called reducible. So it can be split into a product of two non-constant polynomials. And otherwise, we will say, if this is not true, if not true, we say that f is irreducible. So if it's irreducible, it's impossible to represent this polynomial as a product of two non-constant polynomials. So if f can be presented as g times h, then either h is a constant or g is a constant. So this is the definition of irreducible polynomial. So the irreducible polynomials, they're more or less the analogs of the prime numbers. So if you take all the polynomials, f of x, then first of all, you split it into two parts. The first part is the set of invertible polynomials, and it consists of non-zero constants, and non-invertible polynomials. And in non-invertible polynomials, they're split in two parts, reducible and irreducible. And this is more or less somehow a prime polynomials, the analogy of prime numbers. So now, the unique factorization property means that if you take a non-zero polynomial, it can be represented as uniquely as a product of irreducible polynomials and some invertible polynomial, which is a non-zero constant. So, by the way, let me see, should I? Oh yeah, let me give you an example. Well, if you take C of x, the polynomials with complex coefficients, then, well, if you take x minus alpha, where alpha is the complex number, then this is an example of an irreducible polynomial. Well, why it's irreducible? Because if you, well, the polynomial of degree 1 is always irreducible because of this property, because if the degree of f is 1, then either of these guys must have degree 0. it's impossible to have something else. So that's why this guy is irreducible. And there is no other irreducible polynomials in case of complex numbers. This is more or less a theorem saying that every complex polynomial, non-constant complex polynomial, has a root. So that's why every non-constant complex polynomial is divisible by x minus alpha. Now, if we take the real numbers, the situation is more interesting. First of all, these guys are always irreducible, but we also have this case, x squared plus bx plus c, where b squared minus 4c is strictly smaller than 0. So these are all irreducible polynomials in case of the real numbers. The amount of irreducible polynomials depends on the choice of the coefficients. So in case of the real polynomials, these are all possible irreducible polynomials. There are no other irreducible polynomials. This is more or less the prime numbers for the real polynomials. Now, what is the unique factorization domain property? Let me formulate. So the claim UFD. So, well, basically it says that f of x is a unique factorization domain. But what it means? So for every polynomial f from f of x, there is a unique representation in the following form. A times p1 to the k1, that's pr to the kr, where a is a non-zero constant, p1, pr are irreducible polynomials, and ki, they're strictly greater than 0. And unique up to a permutation of these polynomials. So the permutation of the polynomials doesn't matter. It doesn't count. I'm not going to prove this. Well, it doesn't require anything specific. So actually, the only thing that we should use here is the fact that the greatest common divisor can be represented as the linear combination of the initial polynomials. But the proof is lengthy, and it doesn't teach you anything. It just proves exactly what it states. But what is important here is that you can use exactly the same logic when you deal with polynomials as you use when you deal with integers. Because in case of integers, you usually say, OK, you can split your integer into a product of primes. So that's how to compute the greatest common divisor. You just take all the prime factors of the highest degree, which can be found in both polynomials, and that's how you find the greatest common divisor, or you can use any other arguments. But again, the properties of f of x is they are very similar to the properties of the integers. Okay, who thinks that the claim is clear, just in case? Are there any questions regarding the claim? Should I clarify anything? Okay, good. I have 20 minutes. Okay. Should I prove this? I don't know. Okay, let me skip this part, and I want to discuss an interesting thing. Okay, so in case of integers, well, we had this notion of equality modular some other integer. And we have this structure, which is a group of remainders with addition, or ring of remainders with addition and multiplication modular some given integer n. So we have exactly the same procedure here in case of polynomials. So this is called the ring of polynomial reminders. So suppose we have f of x. Now, there are two cases, an interesting case and a trivial case. Let me start with the trivial case. Suppose we are given a polynomial f and the polynomial f is 0. I want to define the remainders modular 0 polynomial. Well, by definition, the remainders modular 0 polynomial, well, they're just the polynomials itself. So I want to define this notation, f of x modular f. So by definition, if f is 0, then f of x modular 0 is just f of x. It's just a trivial case. I just want to define the remainders modular any polynomial. So in this case, I want to define it for the 0 polynomial also. And for the 0 polynomial, by definition, it's just the initial ring of polynomial. It's just a different name for the polynomials. It's not an interesting case. But an interesting case, if we're given a non-zero polynomial. And now I want to define f of x. F of x modular f. This must be a ring. In order to produce a ring, I have to provide you with the several pieces of information. First of all, I have to produce a set. Then, after that, I should provide you with an operation of addition and with an operation of multiplication. And then I have to check that all the axioms of the ring are satisfied. Okay? But first of all, let me produce the set, the addition, and the multiplication. Okay? Now, as the set, this thing consists of all the polynomials of the degree strictly smaller than the degree of f. So this is the set of all polynomials from f of x such that the degree of g is strictly smaller than the degree of f. Basically, this is the set of remainders modular f, because every remainder, by definition, has degree strictly smaller than the degree of the divider. Now, okay, so this is the set. So this is our set. So let's say if f has this form, then f of x modular f consists of all the polynomials of the degree strictly smaller than n. And these coefficients, b0, bn minus 1, they belong to f. This is just an example. So this is the set. So it's more or less clear what it is. By the way, what if f is a non-zero constant? What is this thing? Let's say f is 1. If I take f to be 1, by definition, what is this?
0.
Yes, exactly, just 0. Because every constant has 0 degree. So if g has strictly smaller degree, its degree must be minus infinity, and the only option for the minus infinity is 0. So when f is an invertible constant, this ring consists of the 0 element only. So this is the trivial ring consisting of 1 element. Okay, now, what is an addition? Well, the addition is the usual addition. If you add two polynomials of degree strictly smaller than f, then the result will be a polynomial of degree strictly smaller than f. The degree cannot be greater when you add polynomials. So the addition is the regular addition, is the usual one. Now, what is the multiplication? This is an interesting part, and this is where f should help. Because if you take the polynomials of degree strictly smaller than f, the degree of f, when you multiply them together, the result will, well, the result need not be a polynomial of degree strictly smaller than f. So we should take its remainder modular f. So if we have g and h from this set, then we multiply them, and after that, we divide the product by f with the remainder. Then, by definition, R is the result of the product. So this is how the product works in this ring. So this is very similar to what we did with integers, because how do we multiply two integers in Zn? We multiply them together, and then we take the remainder modular n. So this is the same. We multiply two polynomials together, and then we will take a remainder modular f. And the remainder is the result of the product. So now we have a set, and we have two operations. So we have a set, and we have two operations. Now we have to check that this thing is a ring. So we have to check these axioms for the ring. Well, but I want to skip this. This will be a commutative ring, and this is more or less a straightforward computation. I don't think that's an interesting thing. You can check it, all the axioms here. Okay, but let me give you several remarks. Now, what is the zero element of this ring? The zero element is the zero polynomial. The identity of this ring is just the identity polynomial, which is 1 as a coefficient. Now, what is important, by the definition, this thing is a subset here, okay? No, because just by definition is a subset here. Also, since the addition is the usual addition, this thing is an additive subgroup. So if we add addition, this is a subgroup. However, what is important, if we add multiplication, the left-hand side is not a subring of the right-hand side. So, but it's not a subring. Because the multiplication is different. So nevertheless, it consists of the polynomials from here, but it's not a subring because it has completely different operation, which is multiplication. Well, we're likely to have exactly the same addition, but the multiplication is completely different. Now, okay, I have 10 minutes. Interesting. Okay, I think I have enough time. Now, in case of integers, so how you should think about this thing again. So the analogy the analog of Zn. So if we have integers and we have these polynomials, so these are more or less the same things. So if we have an integer n, we have the ring of remainders here, and if we have a polynomial here, we have this ring of polynomial remainders here. So this is the analogy of this guy, okay? And here we have the Chinese remainder theorem, which says how to split this ring into a product of two rings. So the same thing happens here. So let me formulate the Chinese remainder theorem in this particular case. The grief on your faces, like is immense. It's like you didn't sleep like for a week, and now you have to come here, and like the sorrow inside your hearts, just unbearable, and you don't know what to do. Like, amazing how funny the lecture is. Okay, now the Chinese remainder theorem. Suppose we have two polynomials, f and g. F is a field, f capital I mean, and f and g, they are coprime. Coprime means their GCD, the greatest common divisor, is 1. Now, we have the ring of remainders modular f times g, and we have the ring of of remainders modular f and remainders modular g and their product. And we have a map, phi capital, from the left-hand side to the right-hand side, which takes each polynomial h to h modular f and h modular g, where h modular f means remainder modular f, and h modular g means remainder modular g. So exactly the same map as it was in case of integers. And the claim here is that f is an isomorphism. Okay. Now, who remembers the definition of an isomorphism of rings? Who think that I should recall the definition? Okay. So an isomorphism means that phi is a homomorphism, which means that phi preserves addition, phi preserves multiplication, and phi preserves the identity element. And the second property, phi, is a bijection. Okay? Now, first of all, let's check the fact that phi is a homomorphism. Well, it's clear that if you take the polynomial 1 modular f and 1 modular g will be 1, 1, and this is the identity element of the product. Okay? So C is clear. Now, again, well, exactly the same argument as in case of integers checks that this map preserves addition and multiplication, because the operations modular f and modular g, they preserves addition and multiplication. Okay, so my question is, who thinks that it's more or less clear that phi preserves addition and multiplication? Who thinks that it requires some clarification? Yay. Oh, there was a hand. Okay, so I can skip it. But that's just a straightforward computation using the modular arithmetics. So it's exactly the same as in case of integers. So I just don't want to bother you with this proof. So this is more or less standard. Now, we want to prove that phi is a bijection. This is an interesting part. As you remember, do you remember how we proved the fact that the same thing is bijective in case of integers? Who remembers? In case of integers, we proved that the map is injective, and then we count the amount of elements on the left and on the right-hand side, and since the amount of elements is the same, then injective map must be surjective. So that's why it was a bijection. So here we want to apply the same idea, but the problem here that the left and the right-hand side need not be a finite set. But since F is a field, the left-hand side and the right-hand side is a vector space over F, and it has a finite dimension. Let me compute the dimension. So what is this? This is the set of polynomials of degree strictly smaller than the degree of F times G, okay? As the definition here says. But, okay, if we have this thing, what is the dimension of this guy? Let's check on this example. Suppose we're given a polynomial f. What is the dimension of this vector space? Okay, so who can see that this is a vector space? Okay, if you take polynomials, what is a vector space? A vector space is a set with addition, and you can multiply every element by an element of a field, and there are some axioms, okay? So if you take two polynomials of degree strictly smaller than n, you can add them together, and you will get a polynomial of degree strictly smaller than n. And if you multiply this polynomial by a coefficient from f, you will get a polynomial of the same type. So this is indeed a vector space, okay? Now, what is how to compute a dimension of a vector space? You need to find a basis, and you need to count the amount of elements in a basis. So let's take the powers of x. So 1, x, x squared, x cubed, etc., x to the power of n minus 1. These polynomials are linearly independent by the definition, because a polynomial is equal to 0 if and only if all the coefficients are 0. This is basically the claim that the powers of x are linearly independent. And moreover, every polynomial is a linear combination of the powers of x. So that's why these are coordinates of each polynomial in this basis. And we have exactly n coordinates. So the dimension is n, which is the degree of the polynomial f. So the dimension of f of x modular f is the degree of f. Okay. Who was able to follow this? Okay, good. Are there any questions regarding this? Now, so what is this? This is the set of pairs. In terms of vector spaces, this is a direct sum of two vector spaces. So the basis of this thing is the basis here plus the basis here. So let's count the dimension of the left-hand side. The dimension of the left-hand side is the degree of f times g. And this is the degree of f plus the degree of g. What is the dimension of the right-hand side? This is the dimension of this guy plus the dimension of this guy. But the dimension of this guy is the degree of f, and the dimension of this guy is the degree of g. So that's why the dimension here and the dimension here is the same. Who was able to follow? Are there any questions about this thing? Okay, now, so that's why it is enough, so the dimension of the left-hand side equals the dimension of the right-hand side and equals the degree of f times g. Now, since these two vector spaces have this and by the way, since f preserves multiplication, you can check that, well, f is actually a linear map. Well, it's clear because the operation modular f and modular g, they're just linear. So that's why f capital is a linear map between two vector spaces. How to check that a linear map is injective? We need to compute its kernel as the kernel of a linear map. So the kernel of phi, which is the set of elements such that phi of h gives you 0. If the kernel is 0, which means it consists of the 0 element only, then the map is injective. But if we have an injective linear map between two vector spaces of the same dimension, it's automatically surjective, because the dimension of the image must be the same as the target. So the only thing that we need to check is this thing, because if the kernel of phi is equal to 0, then phi is injective. Now, let's check what it means that the kernel is equal to 0. Well, phi of h equals 0 means h modular f, h modular g equals 0, 0, because 0, 0 is the neutral element of the right-hand side. Now, but this means that this guy is 0, that is f divides h. And this 0, that is g divides h. But now, if f divides h and g divides h, and they are coprime, then their product must divide h. Since f and g are coprime, then their product must divide H. But since H has degree strictly smaller than the degree of the left-hand side, well, the only option is H to be 0. So since the degree of H is strictly smaller than the degree of F times G, then H must be 0. So the only thing that I have to explain here is this implication. Why, from these three facts, it follows that the product divides H. Let me clarify why it happens. But before, give me just 1 minute and I will finish the lecture. So, but before doing that, who was able to follow the last part? Okay. Now, let me explain this implication, why it happens. Well, yeah, this is what I skipped, and I thought I don't need it, but apparently I do. So, well, again, so we can represent the greatest common divisor as this linear combination. And now, let's multiply this by H. Now, we need to show that this thing is divisible by F times G. For that, it's enough to show that each summand is divisible by F times G. But this thing is divisible by F. And since G divides H, this thing is divisible by G. Vice versa. Since F divides H, this thing is divisible by F, and this thing is divisible by G. So this is divisible by the product, this is divisible by the product, the sum is divisible by the product, so H is divisible by the product. So exactly what's written here. So that's why this is true. So again, what we did here, we took an arbitrary element from the kernel of phi, and we checked that this element must be 0. So that's why the map is injective, and because these two spaces have the same dimension, the map is surjective, and that's it. Okay, that's it. The horror has ended. You're free. Okay, thank you guys.